Hi, chemist. It's time to do a lab. So what I suggest you do is go to Canvas, find the chemical and physical changes, or I might say physical and chemical changes lab off of Canvas, and bring it up to your desktop, or you can, print a copy of it so you have something to write down, take notes on. This is a good one. I'm sorry if you guys don't get to do this one yourself, but this is a good one. Most kids think this one's pretty much fun. A lot of fun here. So, physical changes. That's one of the two types of changes we're going to talk about. Physical changes and chemical changes. Physical changes are changes in the appearance of a substance, but they don't change what the substance is. An example, if you change the size of something, you change the shape of something, those are physical changes. If you dissolve it by mixing it with some other substance, you don't really change what it is. Or if you melt it, or it solidifies, it changes from liquid to gas, it boils away. Any kind of a phase change, melting, boiling, condensing, those kind of things, those are all phase changes. Those are physical changes. And kind of the way you tell a physical change is, does the substance change? Does it have the same chemical formula still? If no bonds are broken, chemical bonds between atoms are broken, or there's no new bonds formed, it's a physical change. All right? Compared to a chemical change. Chemical change is when a new substance does form. And that's when bonds are broken and or new bonds are formed. So you're going to have new substances. The substance you start with, the reactants, change into something new so that you get a new product. All right? So if you need to pause right now, what I suggest you do, if you haven't printed off your lab or looked at your lab yet, look at the introduction. Read through that thing and do the pre-lab questions on the front if you're doing that. All right? And then we'll get started. Step number one in the lab, if you look at the procedure on here, we have to be careful. There's some things that we have flame, we have some acid, things could get hot, so we have to be careful in this. In the first part of it, it says to break off a piece of a birthday candle. I got a lovely pink and a blue birthday candle here. So what I'm going to do is I'm going to take the pink one, I'm going to break off a chunk of it, pull the wick out, and I'm going to put that into a test tube. And I'm going to put that back in the test tube rack, and I'm going to start my Bunsen burner. All right, this is a test tube holder. If I squeeze it, it lets it go. If I relax it, the spring makes it hold on to a test tube. So this is the test tube. This is how you grip a test tube with this if you're going to heat it. All right, so let's make sure you guys can see what's going on here. All right, so I'm going to hold this up like this, move to the side a little bit, and what I'm going to do, if you look at the blue flame here, like this, in the blue flame from the side, the light blue cone that you can see pretty plain, that's where the actual mixing of the natural gas and oxygen is taking place. Just above that is the hottest part of the flame. So what I'm going to do is I'm going to hold this wax just above that hot part of the flame, and almost immediately you see the candle changing shape. The chunk of wax in there is changing shape, and it's becoming more and more liquid. I don't know if you can see that real plain, but now it's completely liquid. All right, it's completely liquid now. I'm going to set this back in the test tube holder here, and we're going to let that rest for a little bit, and I'm going to turn off the Bunsen burner. All right, back to here, and then what we're going to do is we're going to light a candle. We already did that candle lab, so we should be pretty good at this. Light a candle, and I'm going to kind of melt the bottom of this so it sticks down like that, and we're just going to let this thing burn off to the side here. So up here we have our melting candle wax, and down there is our burning candle. So we're just going to leave that burn for a little while. All right, so if you need to record any observations, you should be doing that. Number 3, it says take a small piece of paper towel and tear it into pieces and put it on a watch glass. All right, so here is a small piece of paper towel. This is a watch glass. It's called a watch glass because it actually looks like the glass you would have over the face of a watch, like this. This is a wire screen, and we're going to use this to kind of insulate the table from anything that is burning. It kind of protects the table a little bit. Probably nothing would happen here, all right? But I'm going to tear up some little pieces of paper towel and kind of wad them up and put them on here. I'm tearing the paper towel. I'm wadding up. Is it still paper towel? All right, that should do. Then what it says is to set the paper towel on fire and just let it burn. So here comes some burning paper towel. All right, you see light coming from it. You can feel heat coming from it, and the paper towel is kind of disappearing. And what's left is just a bunch of ash. Now there might be a little piece of paper towel that didn't finish burning there, but you mostly get just ash from that. I don't know how well you guys can see that, but there's hardly any paper towel left. All right, if you need to pause and write down some observations, you should do that. In step number 4, we're going to take a test tube, and it says that we're going to put about an inch of water into it. Now, typically in science, we use distilled water. That means there's no chemicals left in it. If we were to, for example, in Norland Park, if you take water from here, there's a whole lot of chlorine in it, and you would get a reaction a lot of times with the chlorine that's in there. The chlorine is there to help keep the safe. The chlorine kills bacteria, kills any germs that would be in the water, but you keep it down at a low enough level that it's safe to drink and it won't hurt you. All right, if you're sensitive to chlorine, tap water for some people could be kind of sensitive to this. So I'm going to squirt about an inch of distilled water into the test tube, and then it says to add a little bit of sodium chloride. Now, sodium chloride is just commonly called table salt. All right, so here I'm going to take this white crystalline powder that's in here, and I'm going to put a little bit of it into the test tube. Then you see it kind of sink to the bottom like that, and we want to mix this thoroughly together. So what I'm going to do is I'm going to use a glass stirring rod to do that. And if I can get all the salt to the bottom and I stir it up really well, and it takes a couple minutes. Well, not a couple minutes, maybe less than a minute. And so now, if I look at the test tube, it looks as though the salt has disappeared. But it's really in there still, because if you were to taste it, it would taste salty. So you know there's still salt in there because you could taste the salt. But it seems to have disappeared. What it has done is dissolved and it's spread out evenly throughout the test tube. Now, how could I tell if I was looking at this if that was salt water or if that was still distilled water? Well, what I'm going to do is I'm going to add something called silver nitrate. Now, this bottle normally would be clear, but silver nitrate turns black when it's exposed to light for very long. And this is a really expensive reagent. A reagent is a chemical that we use to do chemical reactions with to tell something is there. So what I'm going to do, I'm going to be really careful with this. First of all, silver nitrate is toxic, and you need to try to keep as much of this away from your skin as possible. It's not so much on your skin. I've had lots of silver nitrate on my fingers, but if you get it on your finger, and within an hour, your fingers where the little liquid was at is going to turn black. You're going to have a black spot, and it's there until the skin wears off. You definitely would not drink this. All right, so watch carefully while I add. I'm just going to put 1 or 2 drops of silver nitrate in there, and I hope you guys can see that. There's 3 drops, and immediately you can see there's a reaction. It looks like a white, looks like it's separated in here. If I stirred that all up and I mixed it like that, there would be white chunks of solid that weren't in there before. So there's a reaction going on between the silver nitrate and the calcium chloride, or excuse me, sodium chloride that's in the water. And we can tell that there's a new substance formed because you see a white solid that formed. Right? If you need to pause and write things down, do that. Now, while you're doing that, let's look at the candle wax. The candle wax is completely solid. Right? It's re-solidified. It's got a pink color to it. Again, that's probably the coloring from before. But there is, if I turn this upside down, there's nothing liquid going to pour out of it. It's in there solid. If I look at my birthday candle that I had over here, it's about half the size as it was before, and it's still continuing to burn, but there's certainly less candle than there was before. We already know where that candle goes from doing the candle lab before, but it's something to think about. All right, in part number 5, if you go to step number 5 in the procedure, it says take a piece of magnesium ribbon. You guys have seen me burn magnesium ribbon before. There's a magnesium ribbon, and it says to tear it into pieces. Now, this is kind of thick, so what I'm going to do instead is I'm going to cut it into pieces with a pair of scissors, and because this is so thin, just like aluminum foil would cut real easy, I'm going to cut this up. And let's cut one more here. All right, so what I'm going to do is I'm going to take these 5 little pieces of magnesium and I'm going to put it in test tube here. And then what I'm going to do is I'm going to take, move this over here so you can see this a little better. I'm going to take some hydrochloric acid. Now, hydrochloric acid is measured by its strength by something called molarity. We'll learn more about what that molarity means. But this one says, the bottle on it says HCl 6M. The 6M stands for molarity. Most of the acid, the stomach acid, for example, is a 1 molar acid. Most of the acids that we use are 1 molar, so it's not terribly dangerous. This is actually pretty strong acid. So what I'm going to do is I'm going to open this up, and I'm going to put a little bit of acid in here. And immediately you can see what a violent reaction that is. That is really reacting fast and hard. There's all kinds of bubbles being produced. What's making the bubbles in there? Well, there's probably a gas being produced, right? I see steam coming from the top of it. I don't know if you guys can see that or not, but there's steam coming from the top of that test tube. And if I were to touch that test tube, wow, it's hot enough to burn my fingers. It's really hot, all right? So there is tearing the magnesium, and there was putting acid on the magnesium. Okay, if you need to pause and write some things down, do that. In step number 6, I'm going to use this thing. It's called a mortar and a pestle, and it's used to grind up solids, usually crystals like this. So I'm going to set this aside here. This is calcium sulfate crystals. Calcium sulfate is used in ponds a lot of times to kill the algae in here, so you certainly wouldn't want to ingest this. And what I'm going to do is I'm going to take a few of these bright blue crystals in here, and I'll let you look at this a little closer here. Let me move the camera here. You guys can see the bright blue crystals in there and what color they are. They're a nice royal blue, pretty color like that. Don't eat them, all right? And so now you guys have seen that. Let's take and let's do what we do with the mortar and pestle. Now, the way to do this properly is you make a circular motion around it like this, and you grind them up like that. You don't hammer them because you're going to break things with that. So while I do that, let's grind that up. All right, so now what I have left in there is not nearly as dark a blue crystal. You know, there's our crystals from before. They're darker, and this looks a lot lighter. Now, that color change might suggest to you that there was some sort of chemical change that took place, but keep this in mind. What's the color of an ice cube? Color of an ice cube is clear. It doesn't have a color in it. But what's the color of snow? Snow is white. And the reason why it looks white, it's not really white, it's really clear, but it has so many little surfaces on the snowflake, on the little tiny ice crystals, that when light bounces off of it, it gets mixed and it looks lighter and lighter and lighter in color until you see lots of light bouncing off the crystal, so it looks white. Well, if we kept grinding this up, it would probably never get rid of all the blue color, but it would become less and less and less of a blue color. All right, so what I'm going to do next is I'm going to put a little bit of crystal in a test tube. So I'm going to take this powder and I'm going to put it in a test tube here. So I'm going to get some of this so I can get this down here like this. That's in there. All right. Now, what I'm going to do with that, I'm going to set this in here so I can, and let's take a peek at our candle here. Almost gone. All right. So I'm going to need the Bunsen burner again. And I'm going to grab this test tube with the blue crystals in it, the blue powder in it, and I'm going to heat it. Now, as soon as I put it over, there was like a little puff of steam that came off of there. I don't know if you guys can see that, but it's getting kind of steamy looking at the mouth of the test tube here. And there's all kinds of condensation here. And if I look at the blue crystals closer, they're kind of changing in color a little bit. So I have steam coming off of this. And as I heat it up, the blue crystal's turning lighter and lighter in color. So let's see if I can get all the blue off of that. All right, so it kind of turned brown around the edges. I didn't quite want that to happen, but it's a white color now. It's not blue like it was before. It's a white color. So I'm going to let this cool off for a few minutes here. We'll do something else with that. Meanwhile, look at our candle. The candle's just about gone. And it won't take very long for that to be completely gone. All right, so while that blue crystal is cooling off, and I'm going to put some water on it again in a minute, but we're going to look at the next step here. Now, in the next step, in number 7. Now, in the next step, in number 7, this is something that I would do for you as a demo. All right, I have sulfur. The chemical symbol for sulfur is S. It's a yellow solid. This has been ground up into a yellow powder, and it's got a sulfury smell to it if you were to do that. And it's kind of, the powder's kind of sticky. It seems to stick to stuff, right? But I'm going to do another test that we haven't done. I'm going to take a magnet and I'm going to put it to the sulfur, and I want you to notice that nothing is happening when I put the magnet either end of the magnet, north or south. Nothing happens to the sulfur. All right. If we look at our candle over here, our candle is just about gone. And we'll wait. We're probably going to go out here in just a second, so we'll wait. I bet you guys want to make a wish and blow it out, don't you? But it's going to go out in a second anyway. All right, while that's still burning a little bit here, let's look at the other thing. I have got some iron. Chemical symbol for iron is Fe. And this is ground up, and it's called iron filings when it's like that. If you look at the candle, almost gone, almost gone. So we have iron, and they're called filings. The candle just went out. Iron filings, like this. Now, iron is one of the few metals that is actually magnetic. So let's look at this thing and see what happens when I put a magnet next to it. You can kind of see that I can actually drag the iron around. It's attracted through the glass to the magnet. All right, now let's mix these two together. So what I'm going to do is I'm going to pour both of these into a test tube. So there's the sulfur, there's the iron, and I put it in there, and you have kind of a yellow solid. and the brownish gray solid iron, and if I kind of mix those together, sometimes blending two colors, two substances together can kind of give you a different color. So is there any possible way to separate these two powders now? I hope some of you guys thought about using the magnet. All right, so we could actually use the magnet and we could drag all of the iron, or at least most of the iron, away from the sulfur, and we could leave the sulfur at the bottom. All right, so there would be using a physical property to separate two chemicals that are mixed together, physically mixed together. All right, so I want to mix these things up again because we're going to go do something that is actually a pretty violent reaction here too. All right, so I'm going to put this thing in a test tube clamp like this, and we're going to go back to the fume hood. All right, so I'm going to light the fume hood. I'm going to light the Bunsen burner here, get a nice hot flame going. And what I'm going to do is I'm going to heat this iron sulfur mixture in here. Now the reason why I do this in the fume hood, it's going to produce fumes, and they're kind of obnoxious fumes, and also we don't want to set off the fire alarm. So I start heating this, and immediately it looks like there's a change taking place in it. Things are looking kind of bubbly in there, and now there's looks like some smoke coming off of it, like that. Some of the sulfur seems to be melting, but inside, there are things mixing together, blending in there, and if you watch closely, the yellow smoke that was on the top, it's getting sucked back into the solid in the bottom as it gets real hot. So we're going to heat this here for a minute or so. All right, that should probably do. We need to let this cool. And we'll go back up to the front. Now, that test tube needs to cool off a little bit before we do anything more with it. And a matter of fact, it's pretty hot. It kind of scorched the wooden thing on here a little bit. So I'm going to move it up there. Let's go back and look at, this was our copper sulfate. These were those blue crystals, and you can kind of see that it's white in color. Now what I'm going to try to do is I'm going to try to add just a little bit of water, because I see up at the top here there's a whole bunch of water vapor. That's what it looks like. It's vapor up there at the top. And let's see if I can get, like, just put one drop of water back into this. I didn't do this when it was hot before because the test tube would probably crack. All right, and as you can see, as the water hits the blue crystals, the white crystals before soak it up, and it goes back to looking like it did before. So we actually had two things going on here. We drove the water off using heat, and then we added the water back on. It stuck to the crystals, and it turned into a new substance there with that blue crystal there. All right, so now, finally, last thing we're going to do here, let's look at our iron sulfur mixture here. This thing is probably hot. And if I were to take the magnet and put it next to it like this, the iron is no longer magnetic. This became iron sulfide, and iron and the sulfur mixed together, probably iron 3 sulfide, and mixed together, and it's no longer magnetic because it's not pure iron anymore. All right. If you need to pause, do that, but this is kind of the end of the lab right here. And I don't think there's anything left to do except for you guys to decide on there, what did you see? Were you looking at physical or chemical reactions? And then you can answer those questions on there, and I think probably what I explained at the beginning and the introduction should help you with those questions. Good luck.